All right, let's continue what we left last time. Last time we talked about a self ratio test, root test, and an absolute convergence. Right now, let's do a summary of what test do we use to determine whether a series converge or diverge. Okay. Now let's summarize. Now, right now, what do we have line for the test to determine a series converge or diverge is the following. One, the p-test. In which situation do we use p-test? If the denominator, numerator, they are polynomial in n, they are polynomials in n. In this situation, what we usually do is p-test. Okay, this actually, we know p-test says it converges if p greater than 1, diverges if p equal to 1 or and greater than 0. Okay, so this is p-test. Another thing that we did is geometric series test. Geometric series test. Which says if the common ratio, if you find the two common ratio, if you find the ratio of the two adjacent terms, which is independent of the term n, then actually you get a geometric series. Geometric series test says if absolute value of the common ratio r is bounded by 1, which means this means convergent. R greater or equal than 1. This means divergent. Okay, so this 1 and 2, they are they have good symmetry. Then we can actually easily determine their convergence. Then we have comparison test. Okay, comparison test. Comparison test. What we usually compare is, we compare with geometric series, or we compare with p-test using the p-test. Okay. If smaller than convergent series, then it converges. If greater than a divergent series, then it diverges. So this comparison test says, what you usually compare is, of course, p-test and the geometric series test. Then we have the divergence test, which says if the limit of the general term an is non-zero or does not exist. Then the conclusion is then the series diverges. Okay, if divergent test applies, then the series diverges. If you can easily see that the limit is non-zero, then you first apply divergence test to conclude the series divergence, then you're done. And then we have alternating series test. Which says it has alternating factors, -1 to the power n or n minus 1, n from 1 to infinity. And then to apply alternating series, we need to make sure this Bn is decreasing, and its limit is 0, decreasing. So Bn is positive, and the limit Bn is 0. If these two conditions, hold, then we can automatically apply alternating series test to conclude that the series convergent. Okay, when you apply alternating series test, then the conclusion is the series converges. Okay, the series converges. So for example, this you get -1 to the power n, 1 over n, alternating sum of the reciprocal of integers. You can apply, convergent series, alternating series test. So this is convergent by alternating series test. So you can check why or n is decreasing, its limit as n approaches infinity is 0. Okay. And we have root test and ratio test. Ratio test. Ratio test often applies when you have complicated, multiplication of, for instance, n factorial, etc. N factorial. When there's a lot of multiplication, you use ratio to cancel multiplication. And then we have root test. Root test. You have some power, some power. Usually we some powers use root to cancel powers. Root test. Now ratio test and root test, they are both come from comparison with geometric series. Okay, they exactly comes from comparison with geometric series. In this, so what we did is L to be nth root of the thing, and then limit n approaches infinity. Now according to L less than 1, converge. Okay, absolute convergent. L greater than 1, divergent. L equal to 1, it fails. L equal to 1, then fails. It fails. Okay, so this is a ratio test. This is a root test. Now ratio test, actually we did L to be limit n approaches infinity, the ratio of the two adjacent terms, limit of adjacent terms. Same conclusion, L equal to 1, L greater than 1, L less than 1. 3 conditions. So this is ratio and root test. And then we have integral test. Integral test says what we did is actually an equal to the function value at n, such that to apply, so the series is actually considered as Riemann sum. Considered as Riemann sum for the improper integral 1 to infinity fx dx. Okay, to apply integral test, we need to make sure that fx is decreasing, fx is continuous. It's also decreasing. That's it. Decreasing. Then they are, the series converges or converges only if the improper integral converges. So this integral test. So in which situation do we use integral test? Usually we, the function value is actually, we can write down explicitly the function explicitly. We also, remember p-test is actually a corollary of integral test, where we apply fx to be 1 over x to the power p. Okay, so p-test comes from integral test. Actually, p-test comes from integral test. So somehow we already use the p-test. Somehow you can consider, we can also consider p-test as a special case of an integral test. Okay, let's see some examples. Of series. For instance, n from 1 to infinity. This example, n minus 1 over n to n plus 1. Okay, now you see this denominator and numerator, they are both polynomials of n. So you look at the exactly power. So this you should come. So the general term an is n minus 1 over 2n plus 1. Now you find limit of an, and you study the limit behavior of an and compare it with certain things. Now this will be limit n approaches infinity. You see n minus 1 over 2n plus 1. So this by L'Hopital's rule, this actually is limit. You take derivative, limit of 1/2. This is 1/2. Okay. So the 1 and negative 1, they are just really small compared with n and 2n. So when we take limit, it just, does not make a difference. So this actually limit is 1/2, which is non-zero. Okay. Now the limit is non-zero, then we can conclude by divergence test. Okay, by divergence test. So by divergence test. the series of course is divergent. The series n minus 1 over 2n plus 1, because the general term does not approach 0, diverges. Then we're done. Okay. Example. This 1 over n squared plus n from 1 to infinity. Now you see denominator is n squared plus n, which is, which is degree 2, okay, degree 2. Now so what we compare is actually 1 over n squared, okay. Now you see the limit, this 1 over n squared, n from 1 to infinity, it converges by p-test, converges to pi squared over 6 actually. Then you can use limit comparison, or you use comparison test. First of all, n squared plus n is bigger than n squared. So if you take a reciprocal, it is contributed from 1 over n squared. Of course, this is bounded by 0. So by comparison test, the series converges. Okay, converges. Smaller than some convergent series, then sort of implies a convergent. Now, actually, we can find its exact value. For this problem, we have good symmetry, so we can find its exact value. We can find the exact value. Remember, n squared plus n, if you factor it, so this will be n times n plus 1. Now, if you write down the partial fraction decomposition, so you easily check this 1 over n minus 1 over n plus 1. So this partial fraction is very easy to check, this partial fraction. So this series will be, n from 1 to infinity. So this will be 1 times 2 plus 2 times 3 plus 3 times 4 plus 4 times 5, etc., etc. Now, if you use partial fraction decomposition, actually this converges absolutely. So you can change the order of summation. So this is the 1/2, 1 minus 1/2. This is the 1/2 minus a third. This is a third minus a quarter, etc., etc. A quarter minus 1 over 5, etc., etc. Now, you see 1/2 cancel 1/2, 1/3 cancel 1/3, okay? 1/2 cancel 1/2. A third cancel a third. A quarter cancel a quarter, okay? So actually, finally, this is a 1 minus 1 over n, limit capital N approaches infinity, okay? If you do partial sum, then you get this thing. So this actually, limit of 1 is 1, limit of 1 over n is 0. So this is actually, the sum is simply 1, okay? So this, you have good symmetry, so we can easily find it. This is sum is 1. But in general, to find the sum of a series can be hard. Example. K squared over e to the power k, from 1 to infinity. Okay. Now for this problem, remember exponential. So here the ak is k squared over e to the power k. Remember polynomial, the numerator is polynomial square, okay, k squared. Denominator is exponential function e to the k. Remember, exponential function increases really fast, okay? So this actually decays really fast. So decays really fast so that it can actually, it's a sum. You can sum all of them together. It does not, it shouldn't too it shouldn't be too big, okay? So it should, we can sum them, it makes sense, okay? So we should expect the thing to be convergent, okay? We should expect the thing to be convergent because the denominator decay increase really fast. So this thing decays really fast. So here we use ratio test, okay? Ratio test. We use ratio test. Ratio test. So here AK is the thing. AK plus 1 is we replace K by K plus 1. K plus 1 squared e to the power K plus 1. Then take the ratio. AK over AK plus 1 over AK is e to the power K plus 1. K plus 1 squared. And then divided by AK. Multiply the reciprocal of AK. So flip the denominator with numerator. And then we put similar terms together. EK over EK plus 1. Now you can write this as K plus 1 over K squared. Now EK over EK plus 1. You can cancel EK. So you get 1 over E. Okay, so K divided by K is just 1 over K squared, 1 over E. Now remember, we can take limits, K approaches infinity, AK plus 1 over AK. You can take absolute value, but here it's insignificant, every term is positive. So it's limit, K approaches infinity, 1 over K plus 1 squared, multiply 1 over E. Now as K approaches infinity, 1 over K approaches 0. Okay, so this is actually 1 squared. If you write 1 plus 0 squared times 1 over E. So it's 1 squared is 1, so it's 1 over E. Remember, E is, so the value of E, you should know very well, this is less than 1, Then by ratio test, now the ratio is also value of the ratio, limit of the ratio is bounded by 1. By the ratio test, then we can conclude the series, K squared over EK converges. Okay, it converges. Now, of course, we can actually find, this is not bad. You can find it's sum. Okay, you can find it's a close sum. It mimic a geometric series. So you can actually derive this thing from geometric series. Remember what we did for geometric series is we talked about this earlier. So 1 plus x squared, geometric series plus x cubed plus etc. So this is the sum of x to the power n from 0 to infinity. This is the 1 over 1 minus x. Okay, here absolute value of x is bounded by 1. Now if you take a derivative, then you get differentiate with respect to x. Then you get x equal 1, y equal 0. So 1 plus 2x plus 3x squared plus etc. So this is actually n times x, n minus 1, n from 1 to infinity. This will be d dx. The thing. So the right side, if you differentiate, this is very easy. You find it's actually 1 over 1 minus x squared, power rule. Okay, power rule and chain rule. Now, how do you? So what we want is n squared x to the power n. Okay, so now what is the thing? Now remember, if you multiply equation, let's use equation 1, 2. Now multiply both sides of equation, multiply, what do we do? It multiply by x. Multiply equation 2 by x. Then we get x plus 2x squared plus 3x cubed plus etc. So this is actually n to the power x, n times x power n from 1 to infinity. This will be x 1 minus x squared. Okay. Now you differentiate again. Differentiate with respect to x. Then you get actually x you get 1, 2x squared you get a 2 squared x 1, 3 squared x2, 4 squared x3, etc., etc. Then you get n squared x power n minus 1. This is n from 1 to infinity. Now this will be, the right side will be d dx. Sorry, it's x, y minus x squared. Okay, so then you see, multiply both sides. This is equation 1, 2, the equation 3. Multiply equation 3, multiply 3 by x. Then you get x plus 2x squared, x squared plus 3 squared x cubed plus 4 squared x power 4, etc., etc. So it's n squared x to the power n from 1 to infinity. This should be multiply the thing by x, d dx, x, y minus x squared. Now the right side, if you work it out, so this will be x times. So it's a little complicated, but it's still doable. Y minus x squared is degree 4. Then x derivative y minus x squared minus x times this derivative is you use times negative 1. So this you get, this will be x times y minus x squared plus 2x y minus x squared y minus x to the power 4. So this will be x times y minus 2x plus x squared minus 2x squared plus 2x y minus x power 4. So this will be x times, now if you do cancellation, so this will be y minus x squared, y minus x power 4. So finally you use, so this is x times y minus x times 1 plus x, cancel a factor of y minus x, then you get degree 3. So finally you conclude that x n squared x power n from 1 to infinity. So this will be x times 1 plus x, y minus x cubed. Now remember, then we get, remember, n squared e to the power n from 1 to infinity. So you take x to be 1 over e. Okay, here x is 1 over e less than 1. So this you get, this implies this is x is 1 over e. Okay, so this will finally, if you rearrange this, so this will be multiply e cube. So this is 1 plus e, e plus 1. This will be e minus 1 cube. Okay, so then we are done. Now this problem is special. We have good symmetry, then we can actually, because it mimic geometric series, we can use manipulation technique for geometric series to actually to get a closed form of this series. Okay. More examples. Okay, actually we talked about this example earlier. Okay, we did talk about this example earlier. So here this En is 1 over n square root of log n. Now this you can, so here we cannot use p-test. So it's a refined version of p-test. So here p equal to 1, but here we have some factor of log x. So it's a finer version of a p-test. So that we should use stronger tools. So we should use integral test other than p-test. Remember, p-test is derived from integral test. And this stronger version of p-test, so we should use integral test. Okay, so if this equal to, so if we take fx to be x square root of log x, So we have f an is actually the function value of an. Now it's easy to see fx is decreasing. Fx is decreasing. Why? Because the numerator becomes bigger and bigger if x is bigger. So we can conclude that the fraction is actually decreasing. So now we can apply integral test. Now to determine the series an from 2 to infinity, it suffices to study the improper integral x square root ln x dx. Now remember the improper integral we should study. So we actually talked about this improper integral earlier. We use substitution rule. Let u be ln x. Okay, so this will be this ln 2. Dx du will be dx over x. Okay, 1 over x times the dx. So this will be dx over x is du. So it's du over square root of u. So limit t approaches infinity. This will be ln of t. Du over. So this is actually this is the twice square root of u antiderivative. Ln 2 to ln t. Limit t approaches infinity. Now this you evaluate. So this is actually twice square root of ln t minus twice square root of ln 2. And then t approaches infinity. This clearly is infinity. This actually does not exist. It can be arbitrarily large as t approaches infinity. Because ln t approaches infinity in this case, okay? Ln t approaches infinity. So this actually can be arbitrarily large. So this actually does not exist. So this means the improper integral diverges. It can be arbitrarily large. It diverges. Does not converge to a fixed finite number. Diverges. So we can conclude by integral test. Integral. By the integral test, the series actually diverges. Okay, diverges. Now you can also try to do some examples. You know, a final version, n ln n actually diverge. N ln n diverge. Okay, n from 2 to infinity diverge. Now as long as you add a small factor, 1 plus epsilon. Now as long as you have a small epsilon factor, then it converge. Okay, then it converge. So this is actually the boundary between converge and diverge. So this actually diverge. Try to use, you can also use this actually converge. It actually converges. You can try to use integral test to derive these two examples. Okay. Okay. More examples. Now, of course, you can add any more final version. If you n ln n, you can add many factors. So here n start from a huge number. You don't want something nonsense. Okay. Then this actually also diverges. This is the more final version of p-test. Okay, more examples. You can, these 3 examples, you can try to use integral test to work them out. I will not talk about it here. Okay. 3 to the power n times n squared over n factorial. N from 1 to infinity. Here you see we have a complicated product quotient of a factorial and exponent 3 to the power n and n squared. So in this solution, what we usually use is actually ratio test. Okay, we try to use ratio test. So an, the general term is 3 to the power n times n squared over n factorial. And then we find the next term, a n plus 1. So we replace n by n plus 1. 3 to the power n becomes 3 to the power n plus 1. Multiply n plus 1 squared. Okay. Okay, now we find that ratio. We find that ratio, okay? Now an plus 1, we just copy it again. Now an divided by an, so we flip the denominator numerator with flip denominator numerator. But then we group terms that are similar, okay? So n factorial we put with n plus 1 factorial. Now 3 to the power n plus 1 over 3 to the power n. Now n plus 1 squared over n squared. Remember, n factorial is 1 times 2 times 3, etc., to the n. N plus 1 factorial will be 1 times 2 times 3, etc., times n plus 1. So that ratio, you know, we have a lot of cancellation. Now 1, 2, 3, all the way to n, they cancel out each other. So this is actually 1 over n plus 1. 3 to the power n times over 3 to the power 3 to the power n plus 1 over 3 to the power n. So we get 3 to the power 1. Okay, so this is 3. Now this we get n plus 1 over n squared. So this we get okay, so we have n plus 1 here. Cancel a factor n plus 1. So we finally have this is the n plus 1 to the power 1 over n squared times 3. Okay, now you see as n approaches infinity, limit n approaches infinity, an over an plus 1 over an. So this is the limit n approaches infinity, 3n plus 1 over n squared. So this is infinity over infinity. So we can apply L'Hopital's rule. Apply L'Hopital's rule. 3n plus 1, then we get a 3, you know, differentiated with respect to n over 2n. Now, as n approaches infinity, denominator becomes upper third. Numerator is fixed. So this limit is 0, which is less than 1. Then by ratio test, we know. Then by ratio test. By ratio test. By the ratio test, the series converges absolutely. Converges absolutely. Remember, converge absolutely implies convergent. Okay. Okay. All right. This example. N from 2 to infinity. Log n to the power log n. Okay, how do we determine this power? Okay, now numerator 1 has nothing to determine. Now it suffices to study how big the denominator is. How big can log n to the power log n be? This is the question. Okay, remember once the base and the exponential, they're both changing. So what we usually do in this case is, we try to take a line, okay? So let y, for instance, an be log n to the power log n, okay? Now how big an is? So we should have good control of an. So an If we take ln of an, then you get ln n to the power ln n. So this we get, we factor, use the property of ln. So we factor ln n times ln n. Okay, multiply. Okay. Okay. So this will be okay. So this will be an will be take e to the power ln n multiply ln n. Okay, take e. Okay, e cancel ln. E cancel ln. Now this will be e to the power ln n to the power ln n. So this will be n to the power ln n. Okay, it's confusing a little bit. It's a little confusing. Try to don't confuse yourself about the ln n. So actually we know ln n to the power ln n equal to n to the power ln n. Okay. Now you see by p-test, yeah, when n is large, ln n should be greater than, for instance, 2, greater than 2 for n large. Okay. Now you see this will be n to the power ln n will be greater than n squared. Now if you take a reciprocal n to the power ln n, this is less than 1 over n squared. Okay. Remember, this actually converges. The right side 1 over n squared converges. Then back comparison test. This series converges. Then we can conclude n from 2 to infinity. Then we can conclude ln n to the power ln n converges. Okay, converges. Actually converges absolutely. So this problem is a little tricky. Here we need to do some algebraic operation, try to manipulate a little bit with the denominator. Okay. Okay, more examples. This example. Nth root of 2 minus 1. N from 1 to infinity. How big this can be? Now remember, nth root of some number, nth root of a number a. This also a is not 0. This converges to 1. As n approaches infinity. So we need to find how big it is, the difference with 1. Okay, the difference is the 1. So we need to find 2 to the power 1 over n. Subtract 1. How big this can be? We should have a good control of this thing. Okay, we should have a control of the thing for n when n is large. So as n approaches infinity, 1 over n approaches 0. Okay, 1 over n approaches 0. So we can view this by mean value theorem. We can view this as mean value theorem. So how do we do that? So if we study the function f(x) to be 2 to the power 1 over x, Okay. Now limit x approaches infinity. Limit x approaches infinity. Fx should be limit x approaches infinity. 2 to the power 1 of x is actually 1. Okay, now actually the base, what we do is the following. We will try to manipulate a little bit. So we find its derivative. Find its derivative. Okay. Okay, so how big this is? How big this is? 2 to the power 1 over x. How big it can be as x approaches infinity? Remember linear approximation. What linear approximation says? A to the power t for t or when t, a to the power t for near t equal to 0. Linear approximation says we can find its derivative at 0. Then so linear approximation, remember fx can be represented by fa plus f derivative x minus a. Linear approximation. Linear approximation. Okay, so this you can get okay, a to the power t, its derivative is with respect to t is now t is 0. This you got a to the 0, a to the 0 plus f derivative at so here a is 0. So this is actually near a to the power its derivative. A to the t derivative is a to the t ln a, ln a. So this is actually a to the 0 ln a x minus 0, t minus 0, i.e. 2 to the power t is around 1 plus ln 2 times t. Okay, ln 2 times t. Ln 2 times t. Okay, is around. So this is actually 2 to the 1 power x. This is the around 1 plus ln 2 times 1 over x times the 1 over x. Now if you subtract 1, so this actually get this. What you get is it's a little complicated now. So what you get is 2 to the power 1 over x minus 1 is around ln 2 times 1 over x. Of course, it can be make to be more precise by mean value theorem. For instance, if you let t be 1 over x. Okay, now as x approaches the infinity, t approaches 0. So this is actually 2 to the power t, 2 to the power 1 over x minus 1 is 2 to the power t minus 2 to the power 0. Okay, by mean value theorem, then f derivative at some number c, t minus 0. Okay, derivative, so c lies in between 0 to t, 0 to t, 0 to t. Now 2 to the power t, its derivative is 2 to the power t ln 2. Now its value is 2 to the power c ln 2 times t. Okay, times t, where c lies in between 0 to t. Now t, remember t, as t becomes large, t is really small near 0. Okay, so this is the 2 to the power c times ln 2 is greater than 2 to the power 0 times ln 2. So this is greater than ln 2 times t. Okay, so we get 2 to the power 1x minus 1 is greater than ln 2 times 1 over x. Then finally we get 2 to the power minus 1. This is actually 2 to the power 1 over n minus 1. This is greater than ln 2 times 1 over n. Okay, now if we do the sum, nth root of 2 minus 1, this will be greater than ln 2 1 over n from 1 to infinity. Now remember, the right side is a harmonic series. The harmonic series diverges, and then the left side is bigger than a harmonic series. Then by comparison test, the series actually diverges. Remember, the harmonic series diverges. Harmonic series diverges, okay, diverges. So by comparison test, the given series is bigger than the harmonic series, okay? The harmonic series is comparable with harmonic series. The series actually is divergent. Is divergent. Okay, then we are done for this series. Okay. Any questions? Any questions for this problem? All right. Okay. Okay. Maybe one more example. One more example. Okay, now the denominator and numerator, they are both functions of n. Here we have a bunch of polynomials or square root of polynomials. So in this case, what we do is use p-test. Use p-test. You just simply estimate how big the denominator and numerator is. Now, you know, the constant, just look at the highest power. The lowest power is not insignificant compared with the higher power. It's dominated by the higher power. So for the numerator, so you can view it as simply square root of the dominating term is n squared. The denominator is dominating term is n cubed. So this n to the power, so it's n over n cubed. It's 1 over n squared. So it should be comparable. So the order, just simply estimated the order. Simply estimated the order, okay? Estimated the order. Order is 2 here. Then by p-test, by p-test, so here p is 2, greater than 1. By p-test, the series converges, okay? The series converges. Simply just estimate the order of n, the power of n. The series is convergent. It's convergent, okay? All right. Then we're done for this section. Okay, now let's start a new section, power series. Power series. Power series. Okay. The example that we did is a series that it has usually has no variable, Now, actually, we introduce some variable. What is power series? A power series is of this form. Power series. Power series is this form. Cn. C is called coefficients, n from 0 to infinity. Okay, so it is of this form: C0 plus C1x plus C2x squared plus etc. etc. So a general point of view is it's mimic a polynomial. Okay, each term is a power function. So if we stop at the finite terms, then actually we get a polynomial. Okay, so this thing generalize a polynomial. Okay, some examples. Example. we actually already seen a polynomial power series. Example, for instance, 1 plus x squared plus x cubed, etc. plus. This is actually x to the power n from 0 to infinity. We already know this. Okay. Now this actually here we assume x is bounded by 1, x bounded by 1. So this is actually a geometric series with common ratio Vx. Okay, so we can write down the thing. So you see, this power series is simply y over y minus x. Okay, power series. So Cn is called, Cn here is called the coefficients. Cn is called coefficients. Coefficients of x to the power n, x power n. Coefficient. Okay. Okay, power series. You see, for this power series, the geometric series, we want to know when it converges or diverges. Okay, when this power series converge or diverge. So for what value of x, the series converge. For what value the series diverge. Okay, this is a question, convergence of power series. Actually, for power series, this problem has nice answer. Let's first introduce a general version of a power series. Here, the power is to the power x. Okay, x to the power n. Now sometimes this is called centered at 0. Okay, power series centered at 0. So a general version is we translate x by some number a. So we get power series centered at a. Then we get Cn multiply x minus a to the power n from 0 to infinity. Okay, so we translate x by a unit. Okay, so this is the C0 plus C1 x minus a plus C2 x minus a squared, etc. Now we study the convergence of power series. For what values that the power series actually converges. Convergence of power series. Now, actually, we do the following. There are only three cases. There are only three possibilities for power series. For a power series, for a given power series. Given power series, Cn centered at a, and from 0 to infinity. There are only three possibilities. Possibilities. The first one, the given series, the series converges only at point A. Converges only at one point, x is A. Okay, now 2, the series converges for some radius, converges converges on interval centered at a of radius r. Converges on interval centered at a with radius r. I.e., so this is a plus r with a minus r. R is called the radius. Okay, R is called the radius. And diverges. Diverges for all x in negative infinity to a minus r union a plus r to positive infinity. So this interval, so interval I, centered at a. So here r is the interval I is a minus r to a plus r, open interval. Now you may ask what question? You may ask what happened whether the series converges or diverges on the boundary. Okay, so here on the boundary anything can happen. It can converge on the boundary, it can diverge on the boundary. We will come back to this question later. Okay, there's some subtlety on the boundary. Okay, on the boundary there's a lot of subtlety. So I think third case is it converges, the series converges for all x. For all x. Now these 3, 1, 2, 3, you can have a unified point of view. You know, part 1, you can view here r, the radius r is 0. Okay, a point is a circle of radius 0. Okay, a point is a circle of radius 0. Okay. Okay. Now part 2, the radius is actually r. Radius is r. Part 3, the radius, you can think it as the radius is infinity. Okay, the radius is infinity. The radius is infinity. So remark. In case 2, anything can happen. On the boundary. Okay, so the convergence of power series is actually not that bad. So it's totally determined. Okay, so it's convergence. Okay, let's see some examples of all this power series. Okay. Example. Let's see this example. A from 1 to infinity. N factorial x to the power n. Okay, so this is actually 1 factorial x plus 2 factorial x squared plus 3 factorial x cubed, etc., etc. Now, as we explained, factorial increases really fast. Factorial is really big, i.e. Now, for what value of x? If x is non-zero, then the general term n factorial x power n, if x non-zero, then can be big, increases fast. So it cannot be 0. The general term cannot be 0. Then the series, we know the series diverges. Okay, increases fast if x is non-zero. So the general term is non-zero. So this means general term does not approach 0. Okay, does not approach 0. So by the test for divergence, okay, the general term is non-zero, has non-zero limit. Then we actually know the series actually diverges. Okay, diverges. Or you use ratio test. An is n factorial x power n. X is non-zero. Now an plus 1 is n plus 1 factorial x power n plus 1. You find the ratio an over an plus 1 over an. This will be take absolute value. So this will be n plus 1 factorial x power n over n factorial x power n, x power n. If you take absolute value, then what do you get? This is n plus 1. Very easy algebra. Absolute value. This is actually greater than 1 for x, for n plus 1 large. X is the fixed, okay? X is the fixed, non-zero number. So then we can large, simply larger than if x n plus 1 greater than 1 over x absolute value. Then actually we know the series diverges by ratio test. By the ratio test. So now if x is 0, that's easy. If x is 0, simply we get if x is 0, then the series is about every term is 0. Okay, 0 because 0 multiply anything is 0. So the series the series clearly converges. The series clearly converges. Converges to 0. That's very easy. Clearly converges. So in this case, i.e., so this implies the series, the power series converges only at one point, converges only at x equals 0. Okay, so this corresponding to the case 1. Okay, converges at one point. The power series converges only at one point. Okay, more examples. Example. Now let's see some functions that converges at a finite interval. Okay. Negative 1 to the power n, x minus 2 to the power n over n factorial. N from 1 to infinity. Okay, so here we have a power. We have power. Usually what we do is we either use ratio test or root test. Okay, so here we use ratio test. So an is negative 1 to the power n, x minus 2 to the power n over n factorial. Now an plus 1 increase by 1, increase n by 1. And then take the ratio. An plus 1 over an, take absolute value. Now when we take the absolute value, the negative 1 factor, okay, the alternating factor negative 1 to the power n will no longer show up. Okay, their value is 1. So we just simply so we just cancel that thing. Now divided by an, so we multiply the reciprocal absolute value. Okay, so x minus 2 cancel x minus 2, so we get this x minus 2 factor, and then n over n factorial. Okay, so x minus 2 is non-zero. If x minus 2 is 0, this is trivial problem. Every term is 0. Okay, every term is 0. So we are done. So we assume x minus 2 is non-zero. So limit. Now if we take a limit n approaches infinity, now n over n plus 1 approaches 1. So this actually approaches the x minus 2 absolute value. Now by ratio test, we need a so if by ratio test, by the ratio test, if the absolute value greater than 1, it diverges. So if the thing is less than 1, then the series converges. Series converges. You see, x absolute value bounded by 1, so it's bounded by 1 from above and bounded from negative 1 from below. Then we can conclude that x is a 2 plus 1 and 2 plus negative 1. So this is actually this is the 1, 2, 3. 1, 2, 3. So this interval center at 2. Okay, so this is 2 plus 1, we get 3 minus 1, so we get a 1. So it's a center at 2. Centered at 2. Centered at x equals 2. and radius is y. You see, the distance from 2 to 3, the radius is y. Radius y. Now, of course, this is also radius is y. From 1 to 2, so radius is also y. Okay, so the radius is y. Radius is half the length of the interval 1 to 3. Okay, now remember, ratio test fails when the ratio is equal to 1. Okay, so we need to do more work. You may ask, what happens when the ratio is 1? Okay, in this case, ratio test fails, so we need to check what happens when x, minus 2 equal to 1 is absolute value at the boundary. Okay, so of course, if x minus 2 is absolute value greater than 1, it diverges. Okay, this by ratio test. So we also need to check at the boundary. We also need to check the case when x minus 2 equal to 1. Because the ratio test fails, we don't know its convergence and divergence. So we need to check. In this case, we have x equals 1 or 3. Okay, x equals 1 or 3. So we need to plug in what happens if x is 1. Remember the series is negative 1 to the power n, x minus 2 to the power n over n. Okay, n from 1 to infinity. So this power series. If x is 1, what happens? Then the series will be n from 1 to infinity, negative 1 to the power n. 1 minus 2 will be negative 1 to the power n over n. So this will be negative 1 to the power n, multiply negative 1 to the power n. So this will be negative 1 to the power 2n. So this will be actually 1. This is the 1 over n. Okay, this is 1 over n, which is simply the harmonic series. Okay, you see we have the harmonic series. And we know it diverges. So the power series does not so the power series does not converge to the 1. The power series does not diverges the 1. Does not diverges at x equals 1. Now what happens if x is 3? If x is 3, then we get the series 1 to infinity. Now negative 1 to the power n, 3 minus 2 to the power n over n. 3 minus 2 is 1. 1 to the power n is 1. So this actually we get 1 over negative 1 to the power n over n from 1 to infinity. And this is actually the harmonic, the alternating sum of the reciprocal of integers. And actually we know this is the y known. Okay, this converges by alternating series test. Okay, converges by alternating series test. Remember, it's decreasing and the limit is 0, 1 over n. Okay, 1 over n is decreasing and bounded approaches 0. Actually, we know what value it converges to. This is actually negative log 2. Okay, what this is negative log 2. Actually converges to log 2, negative log 2. So it converges at 3. Okay, it converges at 3. So it converges within 1 to 3. Okay, within 1 and 3. And at the boundary 3, it converges, and at 1 it diverges. Okay, so the power series converges for x in 1. Here 1 is open interval. Here 1 open interval. Okay, open at 1. Okay, open at 1 and closed at x equals 3. Okay, be careful. So on the boundary, it can diverge, it can converge. Okay, so we need to be careful at the boundary. Okay, anything can happen. Okay, one more example. Let's see this example. x minus 2 over to the power n over n squared, n from 1 to infinity. Now again, we can use ratio test. We can reuse ratio test. Here an is x minus 2 to the power n over n squared. Now an plus 1, an plus 1. Write down an plus 1. You replace n by n plus 1. And then do the ratio. Use the ratio test to determine when it converges or diverges. Take absolute value. Then what do you get? It's actually n absolute value. Now x minus 2 to the power n plus 1 cancel to the power n. So you get a factor of x minus 2. And then you get n over n plus 1 squared. Now this as n approaches infinity, this approaches, 1 squared times x minus 2 absolute value. So it's actually equal to x minus 2 absolute value as n approaches infinity. This is very easy, okay? It's limit. Now again, the ratio test says we need to let this x minus 2 absolute value bounded by 1. i.e. again, it's x minus 2 from 1 to negative 1. X is from 2 plus 1 and 2 minus 1. So x is from 1 and 3, okay? Bounded between 1 and 3. So what happens at the boundary? Remember, we need to check. We need to check what happens at the boundary. We need to check. Because the case, when, check the case when the ratio, check the case when the ratio x minus 2 equal to 1, i.e. x equals 1 or 3. So we need to check what happens. So we plug in x equals 1 or 3 to the given power series. Then what we get is, let's see what we get. So the power series is x minus 2 to the power n over n squared. Now if we plug in, if x is 1, so what we get is negative 1 minus 2. We get negative 1 to the power n over n squared, n from 1 to infinity. Now you see this is alternating. Okay, it's alternating. So you get, what you get is actually by converges by alternating series test. Okay, by alternating series test. So it converges at 1. So if x equals 3, then what we get is actually 3 minus 2 to the power n over n squared, n from 1 to infinity. This is actually 1 to the power n is just 1. So we get a 1 over n squared, n from 1 to infinity. Now this is actually the famous Basel problem, which is solved by Euler. So this converges by p-test. Actually, we know its value. It converges to pi squared over 6. A really nice number. So you see the power series. So this implies the power series. X minus 2 to the power n over n squared, n from 1 to infinity, converges on 1 and 3, okay, between 1 and 3, both closed, okay, closed interval at 1 and closed interval at 3, okay. Okay, maybe let me just stop here for today. If you have any question, you can ask me a question.
How do you know when to